So let's do another extra example. Let's carry on with light interference, but this time let's apply it to bubbles because there's a lot of really interesting thing there. I guess most people have played with bubbles before. If you have some at home, go grab a set and just blow a few bubbles and have a look at it and see what you notice. Try and blow a couple here. So what hopefully you can see about bubbles is that they have different colors and the colors change all over the surface. So there's a lot of interesting things in those colors, and something we can learn from looking at the colors is we can actually figure out the thickness of that bubble. And that's really interesting. So let's go through that process and see what we can see. When you look at a bubble, you see that it's really, really thin. If you wanted to know the thickness, it would be really hard to measure. We don't really have anything available to us, around the house that can measure things that thin. But you could calculate the thickness just by looking at the color. So let's go through the process just like with the example we did for the thin film on glass, but this time let's apply it to a bubble. So let's think about what we're seeing and what we have when we look at a soap bubble. So I'm going to draw the bubble. So I'll draw a little piece of the bubble wall. So say this piece right here, but I'll zoom in on it. So outside the bubble out here, this is air. So this is air. The index of refraction of air, I'm going to call this N1 because it's the first medium. That index of refraction is 1. The bubble part itself, that's made out of soap. The index of refraction of soap is about 1.33. And then inside the bubble is more air. So back to N equals 1. And that's our third medium, so N2 equals N of soap. So we go from air to soap to air. This is different from the example of the film on glass because there it went consecutively higher values of N. Here we go low, high, low. So we might anticipate right off the bat that this is going to be different than what we did for the glass. Okay, so light is incident on a bubble and orange light is strongly reflected. So the wavelength of orange light in a vacuum is about 600 nanometers. And we know that the index of refraction of soap is 1.33, no units on an index of refraction, and we're trying to find the thickness. Okay, so let's take this, let's draw our picture, let's put the light waves on, let's think about the interference. So I'm just going to draw that bubble once more. Here's my air, where N1 equals 1. Here's my soap. N2 equals 1.33. Then there's my air inside the bubble, N3 equals 1. We're having orange light incident on the bubble. So orange light comes in, coming in this way. That orange light, part of that goes on through and part of it reflects. For this reflected wave, is there a phase change? So let's ask what happens at this boundary. So at this boundary right here, N1 is less than N2. If N1 is less than N2, it's like we're going from light to heavy. So that means that when it reflects, it will invert and there will be a phase change of pi. So on this wave, I'm going to label pi for our phase change. So this goes light to heavy. When it bounces off, it inverts. So this is out of phase from this wave by pi radians. Okay, let's look at what happens at the next boundary. When the light hits the soap-air interface, part of that goes on through and part of that reflects. Now let's ask what happens at that boundary. So at this boundary, we have N2 is greater than N3. So that's like we're going from a heavy to a light. So when it reflects, it stays upright. So the phase change here is 0. There is no phase change when we go from big N to small n. So this wave that reflects back has a 0 phase change. It didn't change phase. So if this one changes and this one does not, then these two reflected waves are out of phase. And we'll think, what do we remember about waves that are out of phase? So if the reflected waves are out of phase, it means that delta phi naught, so the phase constant for each of those two waves, they're different by pi. Like we've been saying all along, the difference is either plus pi or minus pi. So one is pi bigger or one is pi smaller. Okay, so that's where we are so far. We've thought about our incident light. We thought about, does it phase change or not upon reflection? And now people looking at the reflected light right here, they see two reflected waves. Those two waves are going to interfere, and they have a phase constant difference of plus or minus pi because they're out of phase relative to each other. Okay, so now, orange light is strongly reflected. Strongly reflected means constructive interference. So let's write down the condition for constructive interference. So we get constructive interference and we know it's constructive because it says it's strongly reflected. That's the color that we see a lot of. So constructive interference means that the phase difference, so the phase difference between these two waves, the phase difference is given as 2 pi over lambda in the material, so the lambda in the soap, or N2, material number 2, times delta x plus delta phi naught equals m times 2 pi, where m is equal to the integers 0, 1, 2, 3, and so on. Okay, so we're trying to sort out how thick, that's got to be related to our delta x. So let's put in what we know and let's see if we can find delta x. So that's going to be our strategy now, is to try and find delta x. So let's start with lambda. Lambda N2 is lambda in the soap. So that's wavelength in the soap. The wavelength in the soap is the wavelength in air divided by the index of refraction, N2. So we're going to be able to figure that out. It's going to be 600 nanometers divided by 1.33. If you're a numbers kind of person, then by all means go ahead and put this in right now. I'm going to stick with symbols and put my numbers in at the end. Okay, delta x is the path difference. Path difference means how much farther does this wave go compared to this one. This one bounces right off the surface, but this wave has to go in and come back out. So if I call the thickness of the bubble T, and T is a common symbol to use for thickness. If the thickness of the bubble is T, then this one has to travel T, then another T to get back. So the path difference is 2 times T. So that second wave has to travel twice the thickness. Delta phi naught is my phase constant. We said that they were out of phase. So there's a phase difference of pi. in all the problems so far, I've always picked delta phi naught to be minus pi because I said it works out better with the algebra. And I've also always said that it's fine if you pick plus pi. That would also be correct. Why don't we pick delta phi naught equals plus pi this time, just to see that it does still work out to be true. Okay, so for delta phi naught, I'm going to choose plus pi. I would also get the right answer if I chose minus pi. But I'm going to choose plus pi this time. So now let's put all of these things up here and then see where do we go from there. So what I get is my delta phi, my phase difference is 2 pi over the wavelength in the soap, which is lambda, the wavelength in the vacuum or air, divided by n2, times delta x, which is 2t, plus delta phi naught, which is pi, equals m times 2 pi. If we look at this equation, we know everything here, and we want to solve for t, and we know our lambda, so let's start to simplify this equation and see where we get. So the first thing I'll do is I'll take this pi to the other side. So 2 times 2 is 4. 4 times pi times t. N2 is in the denominator of a denominator, so I can bring that up to the numerator. Divided by lambda equals m times 2 pi minus pi. So that's what I've got so far. Let's see, so that's the same as pi outside of 2m minus 1. So I have 4 pi t n2 over lambda equals pi outside of 2m minus 1. I see that I have a pi on both sides, so I'm going to divide both sides by pi. Now my pi is gone. So next I'll solve for t. So t, my thickness, is going to be 2m minus 1 times lambda divided by 4 times n2. So I know I'm going to put in 600 nanometers for lambda. I know I'm going to put in 1.33 for n, but what do I put in for my m? Well, I've got to put in what's reasonable. I know my values of m are equal to 0, 1, 2, and so on. I have to make the right choice. So one thing I'm going to remember is that bubbles are thin. So I want thin bubble. And that will be our standard application. We will look at things that are thin. So I'm going to want a small value of m. What if I started with the first value of 0? Well, if I put in 0 right here, I'd have t equals minus lambda over 4n. The thickness of my bubble would be negative. That's not physically realistic, so I can't choose m equals 0. Okay, next I'll try m equals 1. That gives me thickness equal to 2 times 1 minus 1 times lambda, which is 600 nanometers, divided by 4 times n2, the index of refraction of soap, which is 1.33. Put that through the calculator, and I get a thickness of the bubble of 113 nanometers. So the bubble that we're looking at that reflects orange light, and I saw some orange when I blew those bubbles, that's 113 nanometers. So just by looking at a color, you can tell how thick something is down to the nanometer scale. I think that's actually pretty cool, so that's kind of neat. Okay, so that clues up this example.